Okay, let me see. Something is slightly wrong with my setup here. How odd. Okay. Well, hello everybody. We are talking about molecular computing. And let's see. Did somebody send me an agenda here?
It's in Dropbox, so general box.
Okay. Is it under molecular computation?
Correct. So general box, research
No.
molecular
You don't need to
computation.
tell me the whole
Oh, sorry.
part. I asked you, is it under
Okay.
molecular computation? The answer is yes. Where is it?
Yes. Meetings and then live streams.
Okay. All right. Fine. Thanks. It's the one such thing that's there.
Yes.
Okay. Fine. In general, they're just meetings. The fact that they're live streamed is purely coincidental. Okay. So some of you who were not here earlier, we were discussing in a different meeting something which is just so bizarrely convergent evolution. It's kind of funny.
Okay.
This is pattern matching for molecules.
Awesome.
And this is basically graph rewriting. And for example, this is a quintessential multi-way system, wherever we had it down here, where this is, I don't even know what this is. This is a reaction apply to something or other. I guess that all means do it in all possible, match it in all possible ways. Is that right?
That's right.
Okay. So this is like, it's just a freaking multi-way system. Here it is. These are, so actually I'm a little bit confused here. Why the left-hand sides flip around? Is that just purely for oh, that's weird. Okay, so
you have different. I mean, you have different reactants with different substructures in them that are matched. That can match either, right? So you have.
But basically, what you're saying is, and this is where we're not doing subchemistry. We're doing chemistry rather than subchemistry. What you're saying is, you've got a liquid or something which has a bunch of this guy and a bunch of this guy in it.
Yep.
And then what you're saying is, those can be matched. You can pick those out any way you want.
Yes, these are all the tuples, and both molecules can play both roles in the reaction.
But are
you saying there that you're matching stoichiometric concentrations of these?
No. So I mean, you're just like rewriting some molecule. Stoichiometric coefficients, right? So the pattern or the like the template for the reaction has like a list of substructures that are on the left and substructures that are on the right, and they get transformed into them. And so you search for the first substructure inside the first molecule you give it. You search for the second substructure in the second one. You could give the molecules to the function in reverse order, and you would get a different reaction.
Okay, so I think that's a little different than, okay, so in our world, this would be like a token event graph, and these are the tokens, and the tokens can be picked up. Let's see, the tokens, you go ahead.
In the other notebook, Stephen, the first section has this exact system in it.
Okay, fine.
The Diels-Alder one.
Okay, here we go.
Okay, somebody had already done this and published their multi-way graph of it. And
this is convergent.
They did, yeah, well, it's not convergent, but it can go on forever and ever. I've redone it using our tools, and here is just the first step. The same two molecules there at the top, and the way they can do it. This is a result of doing it for iterations.
What happens if you deduplicate here with molecule isom?
It is.
So these are isomorphic molecules. These molecules are not isomorphic.
Everyone is different. Everyone is different.
Okay. So, but if we made equivalence classes of these molecules, is there a natural equivalence class to make for these molecules?
I'm not sure what you mean by equivalence class.
Okay, so what I mean is, in this picture here, well, maybe these people just didn't go as far as we've been able to go. Perhaps they didn't. My question would be this. Okay, we can imagine, if you're doing graph rewriting, that every distinct twisting and turning of a graph would be distinct. Okay?
Mm-hmm.
But we make an equivalence class of isomorphic graphs by saying those twistings and turnings are not significant. All that matters is the graph isomorphic?
Yes. Okay.
Okay, so in this case, let's pick out a couple of these guys. Let's see if I can. Oh, why can't I edit this? Why can't I get into that? Well, whatever. Let's pick out, I don't know, these two here.
Mm-hmm.
Okay? Which clearly are different. I can see they're different.
Yep.
But for example, if I wanted to get a zoomed out view of this, what is the way of sort of chemical summarization? So for example, one very straightforward thing I can do is just stoichiometry of some kind. Or just, what is the term when you, it isn't stoichiometry. I just want to do like mass spectrometry, so to speak. I just say how many atoms are there in this thing of each type.
Both of those would have the same number of atoms, but in the mass spec experiment, you would get slightly different spectra because the bonding is different and they would fragment differently. But that's probably too much detail.
Well, no, actually, let me understand that.
Okay.
The physics moment, okay, about mass spectrometry. So, I mean, in the original story, you can tell isotopes apart, and you're just fragmenting the thing, and you're just putting the thing in a magnetic field, and you're saying, how do the different atoms,
right at the atom level. At the atom level, the different isotopes will hit the detector at different times because of their different masses. In the chemical sense, it's the same thing. The fragments hit the detector at different times because their masses are different. The two molecules, when they are ionized in the experiment, will fragment differently based on the bond energies and things like that.
So the molecular mass of these two molecules will be slightly different because of
the total mass will be the same. What's called the parent ion would be the same. But the masses of the fragments are very likely different because the composition of the fragments are different.
Okay,
made up of different numbers of atoms.
Physics moment again. Okay, take this thing and put it in a mass spectrometer. Okay, let's be a little bit concrete because now that I'm learning how to do, I'm trying to learn how to do this. Okay, so let me just let's see, let's go. And we need to learn, and we need Emerald friends to be, I'm going to look up their mass spectrometer so that we can actually see what we would actually type in to get, let me just see. Let's go here. Okay, where do I go here? Liquid transfers property measurement.
Spectroscopy near the green bar.
What about mass spectrum?
Oh, they say mass spectrometry. Yeah. There we go.
Yep. Okay.
Okay, an ESI QTOF mass spectrometer. Okay, so let's see, where is the documentation for that? Here we go. Okay. All right. So prepare sample. Okay, we got a little pipette there. Okay, now what does this do? So they're two different, so we ionize the thing. I don't quite understand all of this, but this is how I thought this worked. Yeah, you're just
right. It passes through a
time of flight. Okay, so this one is pure time of flight.
Right.
And that one is given a charge on the ion. There is a certain voltage, so you put a certain energy into the thing, and depending on the, that defines the kinetic energy, but then the velocity is determined by the mass. Is that correct?
Yeah, and the magnetic field determines how quickly they get accelerated as well. In that small, I guess that's the acceleration chamber there in the smaller thing, and then they hit the detector at the other end.
Right. And so here we see the mass to charge ratio. So this is like
Right.
molecular drop type.
Yep. Yep.
Okay. All right.
And each of those lines is a peak, and it represents a collection of atoms, the mass of a collection of atoms.
Okay, but so when this is done to it, what you're saying is it breaks into a the molecule breaks up in some way with
Yes.
cyanide like
Yes.
this, and it
Yes.
breaks into fragments of some kind.
Right.
And
Oh, go ahead.
And one of the things to do is try to take the masses that you observe and figure out what the composition of atoms are that can give you that mass, and then sort of do the reverse do a jigsaw puzzle and try to reassemble what the whole structure is from the, what you can learn about the fragments.
but so unlike, for example, DNA, where when it's broken into for shotgun sequencing, it's broken up, it's going to break randomly at different places. Presumably, when it's ionized like this, it does not break randomly. Is that true?
No, there are some well-known rules about how they break based on the relative strengths of the bonds and structures and things like that. With the case of proteins and DNA, because you're dealing with so many repeating units like that, they actually use the exact mass of the fragments, and then they can tell exactly how many nitrogens, oxygens, carbons, and hydrogens are present, and then which residues they represent. Is it an alanine? Is it a proline? Is it a guanine or a cytosine? And the combinations of those. So that spectroscopy is a little bit different than organic mass spectroscopy.
Okay, here, another one of my these modern, length 1,000 reads that you can get in one of these, nanopory things. How does that work? You're like pulling the molecule through something, and you're watching something as the molecule goes through some membrane. Is that correct?
I'm not sure what you're referring to here.
Yeah, this one's
The technology that the post the newest technology, this nanopore technology for doing sequencing, not the traditional one, not the sort of Gilbert whatever it is thing.
Yeah, I'm not familiar with it.
Okay, all right, fine.
The usual way is digesting the protein and one residue at a time. And
I know. Yeah, right. I know. I think this is something where you're pulling it through some membrane. And the reason I'm bringing that up is in our efforts to study our observer theory and, chemical observers and things, that might be highly relevant, and we should look it up.
I'll look at the nanopore sequencing case for observer theory. Yeah. That's
Okay.
Yeah.
Okay. So just as a sense here, I just want to understand what we're actually, down at the, this is really cool, and we really have to actually use this. Isn't this cool?
Is there click to copy for this? I saw that there was for ones above.
There is.
That's cool.
So all we have to do is assemble a notebook, and we too can do. I know that they have all kinds of checks so that you can't blow up the equipment and things. Because I'd worry about that in my case. All right. Oh my gosh.
Forgive me, are they actually doing the experiment, or is this all computational?
No,
it's real.
It's real. Okay.
And
they've got the instruments, and you design your experiments computationally.
And it's an automated lab, as I understand it too.
Yes.
I was just going to ask if it was. NMR has been doing this sort of thing for a while.
Right. So they have like 200 experiments that they've done this for. That's bad. They shouldn't go back to that. We should.
The good old days.
What?
That picture of that lab.
Yeah, human beings.
But they don't have safety glasses on either. Shame on them.
Probably pipetting from their mouth too. But
was that a thing?
Oh my gosh, yeah.
You mean you suck the pipette with it rather than it having a little bulb at the top or something?
Yeah,
oh yes.
If you were comfortable smoking while you had volatile organic solvents around, pipetting was the least of your concern.
Interesting.
But they were all done, unfortunately.
Yep.
Okay. Okay, so let's take a look back at this. Okay, so what you're saying, what I'm trying to understand is, in a sense, this is defining a, we might call it a metachemical space. This thing, in other words, where are these molecules relative to each other? This is defining that by their ancestry in this picture. That is, okay, but there's also a, what is it, a QSAR kind of space or something, where you just say, like if I, for example, were to draw this out according to the boiling points of these materials, then I would get some completely different embedding, and I would say which things are close to which other things. But I'm trying to understand if you would, don't we have a bunch of these molecular fingerprint quantities that we can compute for these molecules?
We definitely could, yes.
Okay, so in other words, what's happening here, this is telling us based on this, so these events are what? Let me understand what this event is. So this event is the combination, each event.
Yeah, the leftmost event takes 2 of the 6-membered ring molecule.
I understand. Which is a different thing from your intramolecular interaction.
Yes.
This is the intermolecular interaction between identical molecules.
Yes.
Okay. And just so I know, I mean, again, you guys have to humor the fact that I know no elementary chemistry. What's an example of like a really common, you just take copies of the same molecule, like you heat them up and then something different happens when they interact? Is there a really common example of that? I mean, normally when you have a molecule of a particular thing, it'll just sit there in a little test tube or something.
Right.
And because it is in equilibrium.
No, it's because it's stable. It just sits there. Yeah.
Right, but I mean, the things are interacting. Well, okay. So the point is that they may be colliding with each other, but those collisions do not lead to reactions. They don't need to do any rearrangement like this one does.
Right. But if you heat them up, then they have enough energy that when they do collide, that bonds get reformed.
Okay, so what's an example of that?
Bob, would that be just in the simplest case would be just some small molecule?
Yeah, that's something.
That's
okay,
like a drug that would fall apart if it gets too warm in your cupboard in the.
That's
bathroom.
one thing. I'm trying to think of a simple one, something that would have, for example, a carboxylic acid group on it, and you heat it up, and you end up losing CO2.
Just the protein heated. The van der Waals bonds are totally different afterward.
Yeah, but that's a single molecule. I mean, what we're seeing here, you know what we need? We need to see if Theo would actually, maybe if it's kind of random to ask him right now, but if Corey is here, maybe you could reach out to Theo and just ask him if he feels like joining us.
We'll probably have something that explodes.
Can somebody do that, please?
I'll do that too.
Sure.
Right, but so we don't know a great example of that. But will this reaction actually happen in real life?
Yes.
Okay, so what is this molecule here?
It's called yeah, you put me on the spot and I'm drawing a blank.
Can I pick that molecule up here and just type it in? What is that thing? Is that the equals? Which part of this is that molecule?
That's everything. That right there.
So let me just understand. I'm trying to understand our system and so on. Okay, so if I take that smart string, okay, and I type it in as molecule, and it's not going to work, is it?
Well,
why doesn't that work?
Because it's not. Well, it shouldn't. Well, I guess so, but it's not what you think it is. That's a smart string, which means you would give it to molecule pattern.
I know, but I'm complaining. Right, this should work. Why does it not? Because
Well, I mean, that one works, sure, but it doesn't mean the same thing that it meant in a molecule pattern. There are plenty of smart structures that would not work and shouldn't work.
well, okay, hold on a second. A smart structure contains named atoms suitable for transformations, correct?
No, that's separate, right? So, but the smart structure contains something like N or C or S or nitrogen with 3 hydrogens on it, or something like that.
There's
But
a lot of
so there should be a
constraints, yeah.
function. Do we have a function like our isomers function that will just resolve a smart string into all its possible actual concrete molecules?
No.
Seems
I mean,
like we'll have.
right, I agree.
Okay. All right, but then this would work. Then we would resolve that.
Yeah.
And does molecule, when you feed it something, does it should recognize that this is actually a smart string and turn this into a molecule pattern? Do you agree, or is that wrong?
I would have to give that some thought. Like, so normally the idea is that it either
No,
returns a molecule
I think that's
or.
wrong.
You think that's wrong? Okay,
Like integer of string 1 also doesn't make the integer 1.
fine. Okay, but that's going to give an error message then. If I feed molecule something that's obviously not a smile string, it should complain.
Oh, yes.
It
I mean,
does.
right. So in
Yeah.
this case, that is both a valid smiles and a valid smarts. But in the smiles case, it means specifically those carbons have no hydrogens. They have
Okay,
so
how do I
hot
find the
paired
name of this
electrons.
molecule? Can I ask, what do we call it? Molecule name of this?
Right.
This is cyclohexene.
Benzotriene.
It's because there's no hydrogens on it, so it has 3 triple bonds in it instead of 3 double bonds.
So if I say here, I'm just trying to learn how to do this. If I say here, include hydrogens, arrow true.
It still wouldn't, because the string specifically says
They're not there.
Yeah.
Yeah. So
How does it say that?
because of the square brackets,
I see.
it says take what's on the inside literally.
Okay. And is that what it, oh, I see, because it's the pattern but doesn't have the hydrogens on it.
Yeah.
Right. Arguably, there should be a way to transform between these things.
Yeah, we just haven't built it yet.
Right. I mean, so we have been looking into a general converter from a smart string to the Wolfram language representation, but it's and it would cover most cases.
Okay. All right. Fine.
We're not there yet.
Okay.
All right. Okay. All right.
So getting back to your original question, that cyclic molecule that was reacting, it is cyclohexadiene. And you could probably just type in molecule open bracket quote cyclohexadiene.
Which I can't spell. So you.
Well, I'll spell it for you. You can get the cyclohexa part.
Hexa.
D-I-E-N-E. There you go.
That's not the world's most wonderful message, if I might say so. That is almost illiterate. Where is that?
It's not so illiterate to those of us that took organic chemistry 1 and 2.
No, I know, but is ambiguous due to the following. That's the part that it's due to the following.
So that, I mean, that's too much of the raw message that we're getting back, and it could be cleaned up. That's
okay.
agreed.
All right. Okay. Minor point. Okay. Unsaturation of bonds of hex. What does that mean?
So try 1,2 cyclohexadiene. Maybe,
1,3. 1,3 dash.
The issue is
you
where
go.
to put those double bonds, and
Exactly,
there's multiple places for it, so it's not a one-to-one map.
It could have been 1,2, 1,3, or 1,4.
Well,
the
hopefully
message
we
could
can
have been
clean up
clear.
these messages. Yeah. Magnificent. Okay, so there's our molecule. Lovely. Okay, so what we're seeing here is this critter is rearranging itself.
Well, it's joining to another copy of it.
Yeah, I understand. So can we actually see that happen? Let me just save this somewhere. Okay. Can I do the reaction here?
Let's see. If you go to the top of the
Actually-
notebook and evaluate the code section first, you'll have all the pieces. Okay, and then evaluate the line that says deals Alder equals. That defines the reaction template. Okay, and then you should be able to evaluate.
Why are those?
I forgot to paste in those molecules. My bad.
Okay. Can you send me those molecules?
Yeah.
Okay, so let's take a look at what you're doing here. This is pretty cool, actually.
Mhm.
So this here, this is a token event graph where you're taking at every step the two elements that are used in this, the two elements here that are used in this reaction. I can't believe we've never done this thing of highlighting pattern variables in the language, and we have to go all the way to chemistry to realize that's a good idea. Anyway, okay, so here, I don't quite understand why there's this delete duplicate products thing, and I'm suspicious that that isn't going to give the right answer.
No, it does. I just in the chat, I sent you the two molecules.
Okay.
Zoom chat.
Yeah.
Okay.
Okay. Two molecules. Great. Okay. So now this is what we're doing here. I wonder if it's going to be, I wonder how much harder it's going to be to specify for Emerald to actually do this reaction. This would be a good exercise. I mean, we could take these things, right? I believe that when you do it with Emerald, they have a certain store, they have a cache of chemicals, and otherwise you order it from Sigma Aldrich or something.
Yes. Yeah. Yep. And these are real, dime a dozen.
Okay. So then what we would do to do this reaction is we would order this stuff, and then we say, put a certain amount of each of these in a test tube, and then what? How would we make this happen?
Either heat them or irradiate them with ultraviolet light, and the reaction starts happening. And you let it go so long, and then you take the mixture and run it through an HPLC and separate out all the stuff. But it won't stop after just one round. It'll just keep reacting, and you'll end up getting, a great big mess.
Right, you'll end up getting this pattern, this picture here.
You would get a lot of that. Yes, some of these probably won't be made because of 3D geometry reasons, where some things might not be able to get close enough together to react.
Okay, but so normally, I mean, is this essentially like a polymerization reaction?
Sort of.
It doesn't move quite as aggressively as a polymerization, right, Bob?
Yeah, usually in polymerizations, it's again with double bonds, but they're forming long chains. And here we're not forming the chains.
Well, they seem to be getting pretty chainy here.
Well, they are. Yes, the rings are the beads on the chain, which is a little bit different than something like polyvinyl chloride polymerization.
Which has what in the
it's a C double bond C with a chlorine on it.
Okay.
And those double bonds, the double bond, you activate it, and the double bond becomes a single bond, and that pair of electrons from the double bond attaches to another vinyl chloride molecule, forming a single bond between them. And then that molecule's double bond then goes and forms another one to the next monomer that it bumps into, and it just keeps going. And you end up forming a long chain of single bonded carbons with chlorines hanging off.
Now, if we were to, I mean, again, ultimately there are a bunch of ODEs in the normal formulation of chemistry that would tell us the concentrations of these molecules. Is that a true statement? I mean, in other words, there's a rate constant. Each one of these events has a certain rate constant associated with it.
Yep, that's true.
And in general, so if we knew all those rate constants, we could predict the concentration of every molecule here in our, if we knew those rate constants for the given, for the given temperature and pressure and so on, we could predict, given that when we do path counting here, that will give us the stoichiometric, amounts of each of these things. And then we should be able to predict how much of each thing we would get. Am I right?
Pretty much, yeah.
Okay. So from this, but computing those rate constants is really hard. Is that a true statement?
I think so, yes. I don't know if we've got the ability to do that.
I thought predicting rate constants in general was really hard.
Yeah, you have to do methods of initial rates or other, multiple, like you would have to run this experiment at multiple times at different concentrations so that you could have enough experiments to line up with all the variables in those ODEs.
Right, so I understand. So that's a reverse engineering approach where you're trying to deduce from this thing, you're trying to experimentally measure the rate constants, but I'm asking the question
from first principles.
Yeah,
you'd have to. Yeah, from first principles, you'd have to do some kind of electronic structure calculation and calculate the energy of the ground states.
Much worse than that. It's not just an electronic structure calculation; it's a dynamic calculation.
Correct.
I mean, I thought there's these R matrices or whatever they are, which are the chemist's version of S matrices, and I thought that those were pretty out of reach. Or am I wrong?
I'm not familiar with them. I don't know.
Yeah,
I mean, like normally when you collide two molecules and you try and work out what's going to happen, that's in the super difficult to do category, I think.
Yes.
Okay.
Yeah, that would be.
Okay, fine. But then here, up to stereo issues of things, of some of these molecules here might in fact, fold back on themselves if you drew them in 3D. In a first approximation, this is what's, this is a representation of what's going to happen in this set of chemical reactions. Is that?
Yeah.
And all right, so I would love to see an even more minimal case of this, but I think I understand roughly what's going on here. And let me try to understand, what would you, so then there's chemical theorem proving, right? So can we yet do that? Will our existing theorem prover do it?
No. I've thought about that, and I think part of it's a representation thing. The theorem proving thing takes variables, as it were, and we would be trying to do something like trying to prove that 5 + 2 = 7.
Okay.
Where 5 is a molecule and 2 is a molecule.
Right. But Nick, you have method. I mean, like if I picked out this random molecule here, I could absolutely do find shorter,
find replace path, right? Yeah.
Yes.
Yeah.
Would this work with find replace path?
Wait, find replace path takes the list of equalities. You have to form it like the same way as find an occasional proof does it.
I see, but these are token event type structures. So do you have a theorem proving technology that would go, I mean, so what would the theorem want to be? The theorem would be
extracting the proof from this graph.
That's correct. I want to know, these are the two chemicals that I order from Sigma Aldrich and send to Emerald, right? And I'm trying to produce that molecule there.
And you want to find a pathway to it with a known.
Well, I want to find the subgraph.
Yeah.
What I'll basically be finding is a subgraph that ends in that molecule.
Well, that's doable. I have that in the Solvay process example in the notebook.
Okay.
Yeah, that's just graph theory. That's easy.
Yeah, I know it's graph theory, right? But it's graph theory up until this thing becomes giant and has 10 to the 10 nodes. Right. In other words, the question is: are there techniques for finding that path in a sort of logic programming type way that
For this reaction, yes, because the pieces, we're dealing with the same pieces, just be a matter of finding the right combination of the 6-membered ring pieces and the 5-carbon pieces that would fit together appropriately to give you that structure. And
okay, but you're giving me a chemistry answer, and I mean, what we need is a more general graph theoretic answer or something.
Well,
you would be looking for a graph partition.
Okay, but essentially you're giving me a theorem proving strategy that would work for. Okay, so that's a very interesting idea. That basically, normally we have a sort of algebra inspired relation.
Mm-hmm.
What this is graph related relations, so to speak. And I don't think we've
Right.
thought about that yet, unless Nick perhaps has. Of essentially theorem proving. So this is actually, I think Jonathan had a version of this of theorem proving for Wolfram models, which must be the same type of thing, right? Where you're theorem proving, where you're trying to find paths in what am I trying to say? You're trying to find paths between graphs, so to speak, in the space of graphs.
Okay, through a set of rewrite rules.
That's correct.
Yeah.
And then the question is, what are the efficient ways to do that? And I'm now recalling that Jonathan has done some work on that.
Yeah, that would probably be just what's needed here.
Right. So that's kind of what we have to track down. We can ask Jonathan about it. Nick, do you know anything about that?
Well, basically, what Jonathan did is encoding the graph rewriting as an algebraic rewriting. So he had like multiple operators for different arities of hyperedges, for example, something like that. As soon as you encode your replacement rewriting as just a replacement on this algebraic hyperedges, you can just set up like an input for find equation.
I see. So could we do that, do you think? For these molecules, do you think that would work?
It would be like a little bit messy, because if we do it algebraically, it would
well, so maybe that's not the right technique.
Yeah, the other difficulty is annotations on the graph.
Right. By the way, there's a chemistry question from Simon here. Could the rate constants be calculated from the sum of bond strengths?
Well, so I mean, that speaks to the thermodynamics of it, like, right? What heat is
Yeah, but the rate of
reaction
reaction has to do with the difference between the ground state and the transition state.
Yeah,
And
right.
Well,
the
well,
bond
also, I
strengths
mean,
don't give that.
But the bond strengths will tell you whether the reaction can happen or not. Because if the thing is, is that not correct? I mean, in other words, if you've at a certain temperature, if the final state is of higher energy than the initial state, the reaction isn't going to happen unless you put heat in. Is that correct?
Yep.
Right, but then there may be transition states that you have to get to. Well, you can think of it, if you want to think of it in terms of states, there is a transition state you have to reach before you get to the final product from the reaction. But in reality, the concept of a transition, you see, okay, I can translate this into particle physics. Those are called resonance particles in particle physics, where you get to a transitional thing that in particle physics might survive for 10 to the minus 24 seconds. And then it turns into some final thing. Just for my general knowledge, in the chemistry case, when there is a transition state, how long does it live?
Oh, they're
I would guess they're actually probably about the same time frame as the particle physics thing.
Is that right? That short?
No, I think it's auto second level. Auto femto.
Okay, because
minus 24 is a lot, but
yeah, but so that would be 10 to the minus
no,
18.
it's 10 to the minus 18 to 15.
Okay.
Yeah.
And so that then, so wait a minute, are those timescales comparable to? I mean, that's shorter than visible light kind of frequencies.
Right. That's why this experiment is also difficult to do, to watch this in real time.
I see. Okay. But and is it in fact?
That, right?
Go ahead. What?
You can observe this with harmonics. So you get with harmonics, you get in the attoseconds range.
Okay. But is it in fact the case, this is a chemistry general knowledge question, that when a reaction happens, that there are identifiable transition states, or is it just, input comes in? I mean, okay, so at least Michael will appreciate, where it's just an S matrix, basically. Some initial states come in and then final states eventually come out. Go ahead.
No, for some, definitely there are existing intermediate ones that one can identify.
So again, general knowledge question. I mean, in particle physics, there'd be Feynman diagrams that would represent a set of elementary interactions between things. There's nothing similar in chemistry, I assume.
Not that universal.
But the reason is because in particle physics, there's a Lagrangian that says, an electron interacts with a photon, and the electron and photon are both point particles. Whereas in chemistry, you've got these great big things that have a much more complicated, but explain, I mean, you've got extended objects. Okay, this is now, what is the basic physics of that? You have a Hamiltonian for the whole system, but when you have these two big extended objects, you can't think of the interaction Lagrangian in terms of, okay.
It's just too complicated. You could write down a Lagrangian, no problem. You just couldn't handle it.
But in particle physics, there is I think one difference is that in particle physics, each individual electron is just a thing in a particular state. Whereas in chemistry, your hydrogen molecule, for example, itself has a whole bunch of internal degrees of freedom.
Yep, it has a lot of states, and it just blows up from there when you deal with typical organic molecules.
Yes, but I don't think we have the same problem in particle physics. Just we work at energies where we don't care much about the bound states. If we would do this at very low energies, even QED, we would have the same problems.
I see. Yeah, okay. So if you have a bunch of random positonium atoms interacting with each other.
Exactly. They would show exactly the same problems.
Okay, fair enough. All right, okay. So Parmenides on live stream is commenting about using group theory in connection with some of these, I guess, pruning of reaction pathways and so on. And yes, presumably that's the case. That, I mean, it's interesting to think how that is reflected in the algebraic theorem proving methods. That is, that I don't think we do that in algebraic theorem proving, of saying you can't get there from here. Look, we can tell that there's a certain symmetry of this initial tree which doesn't exist there, and so on.
Yeah, and we have to be careful not to confuse the symmetry of the pathway with the symmetry of the molecules on it.
Yep. Right.
Yep.
What does that mean? You mean because the reaction has it doesn't care. I mean, the molecules have, you might have two symmetrical molecules, but they might interact asymmetrically to produce an asymmetric molecule.
Exactly.
But they also might interact in a way that you have symmetry along the reaction path itself.
What does that mean?
So you might have a mirror. So when the two molecules come together, there might be symmetry elements there. So maybe they when they bounce together, they actually have a mirror plane. Or
I see.
Yeah.
So you can increase or decrease the symmetry basically in the reaction.
Yes.
Yeah. I mean, needless to say, it's the same story in particle physics. Okay. Okay. So let's go back. You were pointing me to the Solvay process. I think I understand what's happening here. This is beautiful.
Well, Bob has a few other examples to show still.
Let's take a look.
Well, how many more hours do you want to stay on this evening? This is the same graph, just without the events, just showing the molecules.
No, not the other Diels-Alder examples, but these other two examples, this Wagner Meerwein.
The Wagner-Meerwein, yeah, that's an example where you start out with one molecule and it rearranges and forms a very nice multi-way system that does terminate. There's the first step there. The red atom has a charge on it.
Are these our renderings? They don't
Yes.
look like that. Oh.
It's all our stuff.
Yeah, but I mean, why does this? It just looks, the fonts look different than we usually see. Maybe not. Okay.
Well, I've labeled the atoms.
Yeah.
given
Okay.
them-
Fine. But okay. So
anyway,
then now
yeah.
this. Okay. So this is our friendly molecule. Is that a sulfur atom there?
No, it's the one that has the charge on it,
Oh, okay.
so it'd be easy to spot.
Is that a standard? I see. That's our standard highlighting color.
For the first, yeah.
Mhm.
And that's not the color of a sulfur atom.
And I think sulfur's yellower. This looks more goldy.
Okay. All right. Okay. It's not the color of a gold atom then.
No.
The gold atom at least won't form a compound, so we don't have to worry so much about it. Okay. All right. So that's the molecule. Lovely.
Right.
Okay.
And the bonds, either hydrogens can move, an adjacent hydrogen can move to that colored atom, or one of the bonds to a carbon atom can shift, and then where the bond shifted from, the charge then goes to that atom. And so the example in the token event graph is showing 4 different ways that can happen.
Okay.
And yeah, so they're, I've described the details there about which bonds are moving and where the charge is shifting to compensate.
the good news is we don't need any of these words because we can just see the picture.
Yeah.
I mean, that's interesting. By the way, in terms of step-by-step chemistry, I'm just curious, if we were to put this into Wolfram Alpha with step-by-step stuff, would it be useful to generate these kinds of verbal descriptions of what's going on?
That would be the text for each step. Yeah.
Yeah, pretty much. Yeah.
So with this technology, could we actually, I mean, is it a useful thing to put this into describing reactions in Wolfram Alpha? Is that useful, or is that like nobody cares?
My hope would be that, so in the second semester organic chemistry, you start learning reactions, and there's a small set of molecules that you would feed in as reactants and a small set of transformations that correspond to reactions that they would know at that point. And this is the tools that I would be able to then build automated answer keys to those sorts of things through the step-by-step machinery.
Oh, that's great.
And we would have organic students flocking to this the way you have high school calculus students flocking to
We
this.
already have
I
lots of organic chemistry students.
Right, but no, I remember those organic synthesis problems, right? So, I'm a chemist, but I like being a computer programmer, really. But I'll tell you what, I really like those synthesis problems. It was just like pure logic.
Yep.
It was nice. All
But
right,
basically, this is the underlying. I mean, just like in the end with stoichiometric stuff, it's Diophantine equations and so on. Here, this is the industrial machine necessary to solve these kinds of problems. Is that a fair statement?
Yes. Basically, your question earlier of could you start from your center molecule in the Bob's explosion diagram for the Diels-Alder and go to a particular product? That's a homework problem. Start with this small molecule. Here's your 3 or 4 different reactions that you know. What sequence do you have to do to get to this final product?
Right, okay.
That's a homework problem.
But that's organic chemistry, right? And Orgo only. I mean,
you get that in inorganic too. It's a little bit hairier, but yeah.
All right. So then this technology should allow us to do these. Great.
Yeah.
Always, can always expect to industrialize what was previously done by lots of hand tricks.
Yeah.
Okay. So now you're going on with this token event graph.
Right. And after 9 steps, you've exhausted all the possibilities. And this layout here is just the default one you get. It actually starts at the lower left corner. But the next diagram, where I've removed the events, it actually is top down from the first molecule to the next and going all the way down. And the dashed line represents the demarcation between 2 groups. All the molecules that you see above the line, you will find those ring systems in natural terpene molecules. They're all formed biologically, and the ones below the line have not been observed in nature. And this type of rearrangement is used to produce these natural products, things like menthol and camphor and pinene and those sorts of things.
But so wait a minute, below the line, you get there by just heating in test tubes and things, but no.
You would have to do it in the laboratory. The ones above the line, nature does.
Okay. So, okay. Well, that's very interesting. So this is a terminating rewrite system.
It
basically.
terminates. Yep.
and terminates in that guy.
Yep.
Or no, it terminates in a bunch of loops.
Yes, there are several leaves on this.
Okay, and some of them are cycles.
They would be, yes. Yep.
So let me just understand, I mean, in terms of these reactions, when the thing terminates in a cycle, what actually happens in the test tube, so to speak? Basically, as you put heat in, it just keeps cycling around these different, or is it the case that these things, one of them is higher energy, one is lower energy, and so it will always end up in one of them?
There's that possibility as well. Yes.
But let's say they're of equal energy, or does that not happen? And then is it the case that it just keeps cycling around?
If they're of equal energy, they would keep reacting back and forth if you've got enough heat going in. And then when you take the heat away and it cools down, you'd end up with roughly equal amounts of both.
Okay, so can I understand the chemist's version of entropy? How does that affect these reaction rates?
Mostly only in terms of the symmetry, I believe. Is that right, Jason S?
Yes, I believe so. It would come into the partition function.
Yeah.
But so what you're saying is that, but I mean, that is because of your way of doing counting, that it matters. When you talk about symmetry, you're saying you might generate an equal number of the left and right molecules or some such other thing, and that, I mean, well, don't these reaction pathways account for quotes entropy? That is, when you have a picture, I mean, if we did correct path counting, okay, in a picture like this, I believe are we suppressing the path weights or not? Do you understand what I'm saying? That is, there could be two different ways to get from one of these to another one. There could be two distinct ways to do that, two distinct matches that would allow you to get there.
Oh.
That makes sense? So in other words, you could take your original template and you could do it, left to right or right to left. And it might so happen that both of those give you
Yes. In fact, if you look at the bottom left one, there are what look like two double paths going up to two events.
Yes.
And they both go to the same product.
Yes.
That one there. So it does it two different ways by shifting different bonds.
Okay, so in the token event graph, we are correctly accounting for the possibility. So when I asked about entropy, you're saying that in some sense, the rate of generating events is some fixed rate, but the fact that there are two events here means that there will be more of this product than there would be if there was only a one event way to get there. Is that a true statement?
If it was done under kinetic control, I would say yes. But if you just put them in a test tube and heat them for a period of time, it would be thermodynamic control. And then it would be the free energies of the products that would determine the distribution, not the rate at which they got there, because they'd have time to equilibrate.
Okay, so hold on, let me understand that. So what you're saying there is, if these are two-way reactions, then the story is different. The thing I just described at first is the kinetic case is the case where you're driving it forwards through those events.
Oh, okay.
Yeah.
But what you're saying is that really, but I don't see it. Oh, I see. There is a way to go back from here through that event.
Yes, there is. Yep.
Okay, so then this graph, you're saying that okay, so let me just walk through that for a second. So you say in equilibrium, you've got the forward reaction, the backward reaction, and those reactions have different reaction rates. Is that correct?
Yes, they would, depending on, yeah.
Because, and the reason they have different reaction rates, I mean, the naive reason would be there's an e to the minus beta h term, the e to the minus beta times the energy difference. Is that right? Or is it something different? Or how, together with some other entropy related term, which I don't understand?
It would be the energy difference between the ground states and the transition state.
Yep, the barrier.
The barrier heights, and the barrier heights would be different depending on the direction you're going in, unless the two things happen to be isoenergetic.
Oh, okay, hold on. But the first question is the difference in energy of the final ground states. right? Like your two molecules here,
Mhm.
this one here and this one here, right?
Yeah, they would be different.
Right. So we can compute, and for us, how do we? Okay. Naive question. If we compute the molecular weight, that does not account for that. There's no binding energy. The binding energy is not accounted for in the molecular weight. Correct.
Correct.
It's
Yeah.
just adding up atoms. This is not nuclei. It's not particle physics. The binding energy is small compared to the masses of the particles.
Hmm.
Right. Okay. So
on the edge of what today can be measured on the scale.
Okay. Fair enough. But so what is the quantity that gives you the equivalent of the binding energy? What's it called in chemistry? I just don't know what
it would be the strain energy or the heat of formation.
The change in enthalpy between the two species at 0K, and then if you want to get to the free energy,
yeah, then you had the T delta S.
The T delta
Okay,
S.
all right. Let me just walk through this. At one point, okay. So the enthalpy is the interpretation of the enthalpy is that it's the ground state energies, independent of any temperature terms. Will give you that. That's what determines. Is that what that is?
One more time.
The enthalpy. Is it so? In other words, you've got these two molecular species, and they each have a certain binding energy. And what is the chemistry name for that binding energy? How do I look up the binding energy? Okay, I've got this molecule, okay, this one here, this cyclohexadiene or whatever it is. How do I look up the binding energy associated with that?
Is it the heat of formation?
Yeah, I was just say that's the heat of formation.
There'll be the chemical.
Okay,
yeah.
So let me just for my actual understanding, if I take this molecule and I say what is our name for that?
I don't think we compute that at the moment.
No, we don't. And actually, we were just talking about this the last couple of weeks, ironically.
Okay, but what's the closest approximation to that? I mean, what?
It would be the MMFF energy.
Yeah.
What does that mean?
It's the name of a force field that we have that can compute an energy for a set of atoms and bonds that are bound together. And for the same set, for the same number of atoms of the same types, those energies would be comparable to tell you the relative stability of each of them.
Right.
Okay. So that is the ground state energy. Okay. So now you're telling me the rate that. Okay. So that's the ground state energy, and the most naive. If I was to look at this in thermal equilibrium, why would the relative abundances of those not be exponentials of the difference of ground state, e to the difference of ground state energy divided by kT?
I'm not sure what the question is.
Because of the barrier in between.
Yeah.
Well, the barrier in between. Well, it would depend on what what's happening to change one molecule into the other, and the pathway you take to do it. There are a lot of chemically different ways you could rearrange the atoms and bonds between those two structures.
But hold on. The definition of thermal equilibrium ultimately is you've got a bunch of states, and in standard canonical ensemble world, those states, their relative frequencies are determined by the Boltzmann factor. Am I wrong? So why is that not the case for molecules?
No, it would be, and that's just the difference in the heats of formation then.
Right, but so what I was asking is, in equilibrium, when you're looking at these two species, is it or is it not the case that you can compute the relative abundances of these things in thermal equilibrium by just computing e to the minus the difference of heats of formation divided by kT?
No, because where those yellow dots are, there's another structure that we don't have, and that will have a certain amount of energy, and that's what's determining the entropy.
Okay, let me walk through this, because in standard thermal equilibrium, you have a heat bath, and you're imagining. So, I mean, this is where the chemistry is not admitting that there's a. Okay, I'm a little confused here, because heat gets into these molecules by, they're elastic collisions with other molecules. Is that a true statement?
Right. Yeah.
Whereas
Yeah.
those yellow things are the inelastic collisions that are actual reactions,
Yeah.
right? So most of the time, the vast majority of interactions are elastic collisions that are simply exciting the molecule and could change the internal state of the molecule, but do not change its overall configuration. They don't constitute
Yes.
reactions.
Mm-hmm. No
And-
bond
and-
breaking.
Right. And am I correct in believing that in a typical chemical situation, the only form of heat is the motion of molecules. There's no, when you heat something with a Bunsen burner, for example, that is purely, there's no radiation.
Just adding kinetic energy to the system.
Yeah, right. There's no radiative term. It's just pure. It's pure.
KT, as we would call it.
Yeah.
Right, but it's pure collisions between molecules.
Yeah.
Okay, fine. All right. So then let me understand this thing about these transition states. So in one of these events, you are imagining that event happens by a transition state being formed that then decays back into that, that these two molecules come together, they form some complicated, transitional, clump, which then falls apart again into two other molecules that correspond to the results of the reaction. Is that the picture?
Yeah. Or in this case, the one molecule goes to the transition state where you've got a bond that's sort of between two atoms, straddling them, not settled on one or the other, and then it relaxes back to the original atom to which it was attached to go to the reactants or forward to the product.
Okay, but so now you're saying the thing that's confusing me is normally in the canonical ensemble, all that matters is the energy of the state. And this business about transitions between states in quotes equilibrium doesn't care about any of that, because you're assuming what equilibrium means in the canonical ensemble with a heat bath, I think, is just that you're okay. I'm confused here, Michael.
Well, if it's an equilibrium, the transition state really doesn't come into play unless it's insurmountable. As long as there's enough energy to overcome that.
Okay, fine.
Then the final ensemble will be based on the relative energies of the two different
that's
molecules. Yeah.
But it might be at astronomical large times.
Okay. So this is the part I want to understand. In practice in chemistry, it is not sufficient to know the heat of formation, to know the equilibrium, to know the practical equilibrium concentrations. Is that correct?
As a practicing chemist, we never really worried. I mean,
yes,
we would assume that
you have a piece of iron, and the equilibrium state is not that it's not oxidized in front of you.
Wait a minute. Okay, but hold on a second. What is the traditional chemistry version of if I want to work out how much of this molecule compared to this molecule I have? How do I do that?
Calculate the heats of formation of each and use the partition function or the
Boltzmann factor.
The Boltzmann factor to calculate them based on the
pure
delta
Boltzmann
H.
Factor.
Yeah.
Right. Okay, fine. I think I understand that. But then it doesn't matter a whit what the events are between them in that case.
In principle, yes.
Okay. Now in practice, what happens?
Well, as Michael said, if it takes forever to have that transition happen, the one's not going to go to the other.
Okay, then it's not in equilibrium.
That's right. Then it won't. Well, it would be in an equilibrium.
Technically, it's not in equilibrium. Yes.
Between the two states, no.
What do chemists say about it? Do they call it equilibrium even when it isn't actually in Boltzmann factor ratios?
Yes, they would say it's not at equilibrium, but yeah, it's just that there's an insurmountable barrier between the two.
Okay, fine. Okay. Universe on large stream mass for thermodynamic entropy. Go ahead.
But even in physics, we wouldn't say that a neutron is not in equilibrium because it hasn't decayed yet. Even in physics, we use this abuse.
Right. I mean, in physics, okay, because the issue is different species. Equilibrium is not usually a story of reactions. Usually, I mean, equilibrium in traditional statistical mechanics, equilibrium is like we've got a bunch of particles bouncing around in a box. The fact that those particles might all suddenly break apart is not something usually considered. This is complicated, right? So I see. I mean, okay, one case of this that I remember working out long ago is the early universe case, where, I mean, basically, right. It's a little bit of a hack, right? The way that you get equilibrium between different species, which is what you're saying, Michael, about neutrons. I mean, okay, in a neutron star, this matters, right? You have,
yes.
And then you have equilibrium between, okay, and then we have things like chemical potential. What is the role, okay, general knowledge question here, the role of chemical potential in the discussion of equilibrium for these kinds of things? Is that just I've got a higher number density of one kind of species than another, or what? Boy.
I believe so, right, Jason S?
I was thinking, so because it's the derivative of Gibbs energy with respect to the number of mole. Oh, yeah, with respect to the number of moles. So you're getting, yeah, that's right. That's the right way to think about it.
Okay, all right. Okay, well, this is good. All right, so let's. So I think we understand this. This is a terminating rewrite system. Implemented. I mean, you see one thing. Okay, so the bigger picture here is molecular computing, and
Right.
in a sense, what we have here is a graph rewriting system. So if we can compile our random computation into graph rewriting, then in a sense, then if we have the right events in chemistry, we can compute it. In other words, what to me is interesting is that normally, when I see chemical reactions, I don't normally see, things like this. Normally when I see a chemical reaction, it'll be some pathway and it'll be some, set of things. You don't normally see a complicated, I don't think, at least, you don't normally see something like this, but this makes it seem a lot more like it could actually compute something non-trivial. Or am I getting confused here? I mean, to me, this is, so in other words, if we can compile a computation into graph rewriting, we've got certain graph rewritings that we can do, which correspond to the events that we can implement chemically. Then the question is, if we can compile, given those, okay, okay, the thing that's a little confusing relative to like a Turing machine is we're a little bit more controlled, or we seem a little bit more controlled in a Turing machine or in a expression rewriting system, because we've got this tree in a definite order. Here, what do we have? What is our input here? Our input is, well, how do we determine the input other than by just saying we've got these chemicals and these concentrations? If that makes sense. Like for in the case of an expression, a combinator expression, let's say, or let's take a combinator expression as an example. We imagine that the input is, S of K of S of S of S of whatever it is, right? We got this long, essentially combinator polymer, okay? And our long combinator polymer is the initial condition, and it goes crunch, 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 and does all these reactions, so to speak, and then comes out with a result.
Yeah.
Okay, so my question would be, what would we imagine that if we just think about things in liquid phase chemistry, which is, I guess, what this mostly is. Is that right? I mean, these reactions are mostly liquid phase.
Yeah.
so, what's the preparation of an initial state in liquid phase chemistry? In other words, if, for example, we were able to, let's imagine that we could make a graph transformation that actually is the combinator reduction. Doesn't seem totally impossible that one could do that. Right. So in other words, we've got to have something where, KXY, and well, I don't mean a potassium there. I mean a K combinator.
Right.
But who knows what the K combinator, the K combinator might actually be some little, residue-y type thing, together with two, slots, two arbitrary connected slots, X and Y, and then basically we would have an event reaction where it turns into X or whatever. I mean, that would be how we would implement a combinator chemically. But the question would be, if we want to prepare the initial state, how would we do that? In other words, if you want to just make a molecule, so I mean, clearly in biology, we've got ribosomes and things like that go and extrude molecules. Is that the only known way to kind of custom make? I mean, this is sort of the problem of ultimate molecular manufacturing. How do you make an arbitrary molecule? But we're not asking for an arbitrary molecule. We're asking for something that is extruded a bit like a ribosome extrudes things, potentially. How can you make a molecule whose structure is specified programmatically, other than with biology?
There's just a Nature paper about it from UFL people today.
Okay. What does it say?
I haven't read it yet.
Okay, but it's some heteropolymer type thing.
No, it's smaller, but it makes things we couldn't do before.
Is this the one with the bowl and the ferrocines?
I don't think so.
Okay, then I'm thinking of a different one.
Let me find it.
Yeah, you'll send that around, right, Michael?
I think I sent this morning.
Okay, but then I hope I'm on whatever mailing list you're sending it to, because I don't remember seeing that, but then I wouldn't necessarily know yet. Okay, but you see where I'm going with this. I mean, so the question is, can we prepare an initial state? Because having a bunch of molecules just floating around based on their concentration is not going to be enough to specify the initial conditions for a computation. It might be enough to have these molecules kind of, I don't know, if we have some kind of chemical observer that's kind of arranging molecules on a membrane or something. Okay, so here's another question. I mean, is the right thing to do to try and imagine assembling a molecule which then in liquid phase has things happen to it? Or is the right thing to do to try and assemble a molecule on a surface and have things happen to it?
If you want it very controlled, then the surface would be the way to go, or some other kind of matrix.
Okay, what's an example of where you assemble a molecule on a surface or in a matrix?
Perhaps forming a crystal of something and then irradiating it, and the bonds happen to be in the right juxtapositions that they rearrange and form, new bonds between the molecules.
Well, okay, so for that, the other project my random crystals project is relevant. That is, can you get a set of things which arrange themselves in okay, so what you're saying is, which I think seems very difficult, that is, if you have the right matching conditions, you can end up with something that
I think an example would be that pentadiamond paper that came out a year and a half ago.
But there are pathways which take a long time, which takes like days, right? Look at what you need for making the vaccine. I mean, they need days for certain reactions to happen.
What was the thing there? What's the point there?
So it's not just there are other conditions which you have to consider. It's not just, I mean, you cannot solve these things from first principles. That's why the chemical industry is such a big thing, because they have to find these things. But if you look how they do the vaccine, I mean, they take reactions which takes weeks to do, right?
Which reaction takes weeks?
There are certain ways how they prepare some of these COVID vaccines.
But which part of it? The lipid nanoparticle part, or not the RNA part?
No, but some parts they take quite a long time. That's why it takes so long to develop the vaccine. It took so long.
Well, vaccines that are killed vaccines or partially killed vaccines, they have to grow them, and they get produced inside of, the virus gets produced inside the host cell
No, I don't think it's that, because they said certain chemical reactions would take days or weeks and that's why.
That has to be the coat, not the. I would think. I mean, otherwise, well, whatever.
Yeah, I mean, if you apply heat to make it go faster, you probably end up denaturing things, and that's why they have to do it at room temperature or colder, and then it's slow.
But chemistry. So I mean, that's why the chemical industry is really a big industry, right? And it's not that. I mean, starting from first principles, I think it's a little bit naive picture here. So.
Well, the software industry is a big industry too. I mean, it doesn't mean that you can't make up a, you can't have combinators that can do all of software.
But there are certain companies which went through the literature and collected all the chemical reaction published, and now they're using this for synthesis, and they're selling products.
I'm well aware. I know that's been a long running, that's been a thing which people have tried to do since the 1960s, right, when the first applications of automated theorem proving to chemistry were done.
Now, hold on. Stephen, you were making a comment about molecular computing a while ago, and then you asked this question about the initial condition. How do these go together?
What I'm saying is, if we could construct the initial condition, then could it be the case that, I mean, this is like a quantum computation. We've got exactly the same problem. We've got a whole bunch of pathways here, which are computing a whole bunch of things in parallel.
Yes.
And we've got to figure out what's the answer.
Well, this is just a reaction cone. It's like an entailment cone.
Yes.
But for chemistry.
Yes, that's right. But yes, the point is that the observer here, exactly the same type of problem as with quantum mechanics. Let's say this was factoring, let's say this was computing products of numbers, okay? And we want to find out, let's say we had something here, and that would be an amusing case to look at, in which we've got an encoding of numbers in these molecules, and we're computing the, each one of these paths is a different product of numbers, okay?
Fine.
And so somewhere here is the number 1, 2, 3, 4, 7 or something that we want to find the factors of, okay? And the factors will correspond to the path that gets to that molecule.
Yes.
Okay?
Yeah.
Okay. So now, go ahead.
I miss to see where the quantum mechanical part is.
There's definitely it's an analogy. No, Michael.
There's a classical field involved.
The whole thing is a classical system. This is a classical system.
Good. So it has zero non-trivial effects.
Yes, the H bar is 0 here. Okay.
Okay. H bar is 0.
I mean, we don't have entanglement on any of the interesting things in the world.
Well, let's take a look at that.
I think this graph is interesting, Michael.
I'm not certain that we don't have entanglement. We don't have quantum entanglement, but we have a different kind of entanglement.
But hold on, Stephen. You were saying we want to find a particular path.
Okay, so let's say we're trying to solve the problem. We're trying to use chemistry to factor a number.
Okay. Yeah.
So we put in our molecules. They compute all these different possible paths.
Yes.
One of those paths correctly generates the number we want, and we say, look, this is a factoring of that number. Okay.
Okay.
The problem that we have is there are many paths, and to find the one that we care about is not trivial.
Yes.
So in chemical synthesis, what one would say is the yield. Normally we would say there's lots of detail that we have to put in to increase the yield. Right? We don't want all this other stuff here. This is, as we run this thing, most of the molecules, most of the reactions happening in our test tube are irrelevant, because the one that we want is just this one that's going to make that particular molecule there. Right? So we could, if we were doing synthetic chemistry, we could spend a lot of effort increasing the yield that would lead to that particular molecule we want. But the reason I'm making an analogy with with quantum mechanics is, at least qualitatively, in a sense, when we have a quantum computer, the concept of what's going on is that we are, we're following all these paths and they're all happening in parallel, which is exactly the same as what's happening here.
But it would be, no,
Yes,
I'm still not convinced. It would be like the factoring algorithm you do with light and gratings. You have a classical one that you can follow. You're allowed to look inside in between, which you couldn't do in quantum mechanics.
Okay, but what if you have some physicalized observer, not necessarily a membrane, but something like it, that could provide some indication, when the path that we're looking for is being, passed through that,
it's
physicalized. Yes,
there's some sieve at the end, and that's and when the thing falls through the sieve, then it's the answer. The problem is it's non-trivial to make that sieve, I claim. And I claim that that's the analog. I'm not completely certain of this, but I claim that there is a potential analog of that problem in the can you look inside problem. That is, that as soon as that sieve could, by mistake, sieve something in the middle here, you're kind of toast. You can't get all the way to that answer. Michael, if that made sense. In other words, you've got a thing that is trying to observe stuff here.
Yeah.
And can you make an observer that doesn't mess with the stuff inside here, but only nails it when it gets to an answer?
Well, the other point is that if the sieve is being placed at some parent node, the pathways are still ramifying. So you can't put it there.
Well, I know, but the sieve, look, physically, there's a bunch of molecules bouncing around in a liquid. Okay?
Yes, I understand.
And the way that we measure them is ultimately, how might we measure them? I mean, what we might do, for example, let's say we had and I don't know my what is it? I don't know, ELISA thing or whatever the heck those things are. Those things where you have little attached, what are those things called? Where you have attached little peptides that on a plate, and then things bind to them. What is that?
That's ELISA, I believe.
Yeah. Okay. Fine. Okay, but I mean, so that would be an example here of where we've got those little things hanging off off the side of our test tube. We have a bunch of little attached peptides, and then when we've got the right answer, we bind to those. The right answer molecules bind to those little hanging peptides. Right. And then we take the thing out and we do we measure it with some ultraviolet light or something. Okay, so that would be an example of what of the workflow here. That is, we put the things in, we have to prepare the initial conditions, which I don't understand how to do. We heat the thing up, it does all the things it's going to do. Then we have our little place where we stick into this test tube a little thing which has all these little attached binding things on it. Yeah. We pull that out, we see whether anything bound to it. That's our experiment, so to speak. That's how we try to get an answer.
So the thing is, in terms of the meta models, the initial conditions, obviously, it's not confusing at all, right? I mean, you can use causal graph, branchial graph. We know what the initial condition is. Are you saying methodologically, in terms of a lab, it's more difficult?
Yeah, I'm saying I have no idea how to make the initial condition in a lab.
Okay.
That's because I think the initial condition has to be a configuration of molecules or a particular molecule. In other words, if I took this picture and instead of that starting with a very simple molecule here, I were to start with some kind of heteropolymer thing and then have all these reactions happening on that, that will be a case where I can give input, like I can give the initial combinator, and then it's going to do a bunch of reductions. And the reductions will correspond to the multi-way graph that represents all possible evaluation paths for the combinator. And then the issue is, what is the answer? How do I sieve the thing to get the particular answer that I want? Now, in the case where the thing terminates, it's fairly easy, right? In the case where it's confluent, it's fairly easy because if it's terminating and confluent, then it's all easy. Then in the end, you just keep heating you start off with your initial combinator molecule, you keep heaping it up and stirring it and whatever else. And in the end, you've got this white powder left over, and that thing is your answer.
Well, sure. Foliations and the observer really, they don't matter for something that's completely confluent.
Yes, but I mean that was the case where you had, except for the fact you had multiple final states in your example, wherever it was. In your example, where in this example here, you have ultimately, but the difference here is you have multiple final states. Right? You have, in this picture, in the physics terminology, you have closed time-like curves here. You've got molecules that are cycling around, as opposed to it's just a partial order, and in the end, you get a single molecule out. The notion of time is not recognizable in this picture because you have cycles. Icon.
Yeah. And there are related systems to this where everything ends up being just one molecule in the end. You can start with almost anything and let it go. And because of the stability of the one particular molecule in the network, everything ends up there no matter where you start.
I want to see an example of that. That would be really nice to see.
It's adamantane rearrangements or diamantane.
You have that.
That's
here?
one of the, I don't have that coded up yet. That's one I want to do next.
Okay, but fine. But you're saying that purely combinatorially, all roads lead to the same answer there. It doesn't require anything about, energies of transition states or anything like that.
No, because the reaction conditions are such that all those barriers are overcome.
Wow, that's cool. I want to see that. That's a chemical black hole. I mean,
Effectively, yes. I can send you some publications from the 70s and 80s that were looking into that.
Okay, all right. Let's take a look at some of the other things that are here.
Let's go to James's stuff.
Okay. Boy, I'm impressed that James knows anything about chemistry. I'm okay.
Well, Wolfram Alpha certainly helps.
You're welcome.
Okay.
Yeah, thanks. Thanks, guys.
Yeah. Okay. So you are trying to make
soda ash.
Soda ash. Okay. What is that? Is that used for fertilizer or something? What is that?
I have no idea. Bob, why do we want soda? Why are we doing this in the first place? Why do we want soda ash?
It was just somebody at one of our previous meetings gave a diagram.
When I say
we're
why
asking
are we
a
doing
general
this,
knowledge question.
When I say why are we doing this, I mean, why did this Solvay fellow even decide to, do this? Why do we want soda ash? Why is it useful?
Okay, which one is the soda ash is sodium carbonate? Probably is a way to produce sodium carbonate that would be used as a reagent in in some other chemical process to be able to get it from some starting material.
Actually, I looked this up here. It says soda ash has a number of diversified uses that touch our lives every day.
Yeah, glass manufacturing.
Use it for baking.
Cooking, food additives.
Well, usually it's the bicarbonate form that's got.
You need it for pretzel. You need it for pretzel. You have to.
You need it for pretzels.
Yeah, you have to paint the pretzel. Otherwise, it will not get the nice.
Okay, well, this is important. This is important. Obviously, if pretzels depend on them, yeah.
Okay. No, the pretzel you get for broadside. The one, the big one.
Okay, so let's.
Okay.
So this is sodium chloride and calcium carbonate.
Yes.
And
we end up getting soda ash and calcium chloride.
Okay, so what are the underlying rules here?
All the ones up top.
There are tons of them.
There are a lot, especially when you specify them all in detail. There are many rules.
Okay, and this is the fully deduplicated graph.
Well, okay, technical question for Nick. So Nick, you have 3 settings right now for these token event graphs, right? You have token deduplication, true, false, and none. So this is false. What's the difference between false and none? That option for the tags right now.
So false means you only deduplicate on each time slice, and none you basically
deduplicate across all.
Deduplicate not at all. Yeah, you just add a unique index to each token.
Okay, so this is deduplicated, goes to false. for the.
So that means there are
time
two
steps.
sodiums here, right? So at different time steps. So if we deduplicate it all the way, so if we open this up, I don't know whether we can do this here, and we do duplicate it all the way, then we would only have one sodium there.
Yeah,
Correct.
I had some problems with that deduplication though, which is why. I didn't
How do we
do it.
set that? Yeah.
It's just token deduplication. If you just go up to the right, right there.
Yeah.
Yeah, but
Make
So what do I
make that
say?
none.
True?
well,
None. Oh,
none.
None.
true.
that-
True. Yeah, you want complete deduplication.
Well, but it's not going to work because the highlighting, when you have it as token deduplication goes to false, you specify the tokens in a different way when you do the
Okay, fine,
highlighting
but
graph.
the highlighting is
Yeah.
wrong, but the final output.
Yeah.
So I don't quite understand what this is doing. So this is saying we get as output calcium chloride
Yes.
and ammonia.
No, and soda ash, but this
But that's not soda ash.
I know.
so am
but
I-
look
what-
at the arrows. The arrows are going up. This layout is this.
Oh, yeah, all right. So
Layout is not
let's say graph of this. Graph layout goes to layered digraph
Okay.
embedding.
Nope.
That's still giving the same thing. But
Yeah.
so,
Yeah.
and why on earth is that H2 italic? Very weird.
That's weird.
That's a small baguette.
It's a single letter before the subscript, and that's
know,
why it gets
I know.
italicized. Whereas in carbonate, you've got CO
Yeah, I see it.
before you see the subscript.
But what about with the
Okay, anyway, there's a minor bug there.
NH3? That's kind of weird. Anyway,
It's because it's
Because
NH. It's two letters.
There's two letters.
oh, I
It's
see.
just a
I get
baguette.
it.
It's not two atoms. It's two letters.
Yeah, okay, okay.
Right.
Yeah.
Okay.
Yeah.
So, okay, so what are we learning from this? So this is a thing where if we included path weights,
Hmm.
we would get, I believe, the whole. No, okay. Explain the. Okay. If we wanted stoichiometry, we would have to do something where we, like a Petri net, we consider different kinds of what Petri nets call tokens and how that flows through this graph. I mean, this would be a Petri net, if I'm not mistaken, if we actually put, constant amounts on each node. Am I right
Mhm.
about that?
I think so. Yeah.
Okay. So it's essentially a de-stoichiometrized Petri net, whatever that might be called. Okay, but that's cool.
Subchemistry Petri net.
It's a subchemistry Petri net, yes, where it doesn't care about the total concentrations. It
That's
just
right.
cares about what the molecules actually do.
Here's about all the rules, right?
Okay, so what's this? What are these colored lines here?
Well, so the overall reaction is sodium chloride plus calcium carbonate goes to soda ash and calcium chloride. So I want to have arrows between the left-hand sides and the right-hand sides of this reaction. So you have your paths from calcium chloride going to soda ash and also going to calcium. Sorry, you have it from sodium chloride going to calcium chloride and soda ash. You also have your paths going from calcium carbonate to
Right.
those two outputs as well.
But it seems to me that while we talk about a single reaction path, this is more like the metamathematical case,
Mhm.
where what we really want, just like in the metamathematical case, we didn't, in the end, to prove a theorem, we end up with a whole, passed light cone that
Yes.
contains certain inputs and then puffs out into a bunch of simultaneous lemmas
Yes,
and then comes back down to the final state.
I'm just calling those reaction cones. Yes, right.
Okay, but now are we seeing a reaction cone here, or are we seeing? We're seeing. I mean, this.
No,
yes,
it's
we
much.
are.
It's kind of much dirtier than that, because what we had in metamathematics is we had two-way rules, and so the kernels, as I call them, like the cores of those entailment cones, were it could just be one two-way rule, for instance. Whereas here, I have to specify many, many, many rules in order to get this industrial process to work. So it's not a kind of a clean reaction pathway that kind of just takes care of itself, it seems I have to specify many rules to get this to work. So I don't think it's a good example of what we want in terms of a reaction.
Listen, this is an engineering example
Yes.
where, I mean, this thing, if you just kept it running, right? If I ran this for another step, nothing else would happen. Is that a true statement?
No, I think it keeps going.
Well, let's see it.
Yeah.
So if I do this and I go, where's the number? Is that 4 the right number?
Yeah.
And this, of course, doesn't have its full deduplication. But is it going to make any other species?
No.
Okay, so if it was fully deduplicated, in the test tube, nothing turns green or whatever. You know, it's not like eventually there's some weird other compound that's produced.
There are no surprises, no.
Right,
but that's because of the way that these rules have been specified, right? Because it's not like I'm doing bond atom pattern matching. I'm just specifying these molecules.
I get it,
right?
But my point is, this is traditional engineering in the sense that the thing has been heavily constrained, so that it can really only do one thing.
That's right.
Yes. Okay, so I claim that the 2 examples that we have, well, we have only one example right now. The only example we have of molecular computing is life. And quite possibly life is making use of things which are not as deeply constrained as this. Or maybe it did at the beginning, at least. And what we want for, the interesting case of molecular computing is the case where you really can do this kind of elaborate stuff, where you really can get it to do that number of computations. It is not the case where in the engineering situation where you've optimized the synthesis pathway and you've put all these protecting groups on to stop different side paths happening and so on, and you have most of the action going on a single pathway. That's exactly what we don't want. We want something where you can do more like sort of the promise of quantum computing, where you can do a lot of things in parallel, I think.
Yes, well, and also we want to be able to capture computational work, which will be irreducible. And I don't think we should put that many constraints on it. But the difficulty is going to be the observer theory question, especially if, as you said before, the kind of fundamental objects of these computations will be paths rather than individual tokens. How to be able to capture, irreducible computational work from these using some observer theory technologies without always being able to anticipate what those paths will be like.
Well, okay, but one possibility is the answer is the molecule you make, rather than the answer is the journey by which you get there.
Yeah.
Well, okay, but that's kind of different from what
I know. It's different from what we've discussed before. I mean, what we've discussed before is is what kind of information is contained in the path structure, right? So one type of information is what molecule got made.
Well, sure.
So where did you end up in metachemical space?
Yes, right.
Or and the other is, what path did you follow? And by the way, I mean, I assume there are geodesic and non-geodesic paths. There must be, yeah. I mean, there clearly are, because you can clearly, in a lot of these reactions, you can clearly cycle around forever before you end up getting to the thing you want to get to. I mean, there's a geodesic path from the initial state to the final states, which is the minimum length synthesis pathway. Am I right?
Yeah, that would, I mean, you should be able to find a minimum path between your starting node and your desired final node.
That's right. Often not the most efficient way, right? To go.
It's not necessarily the most efficient, but I mean, in practice, I'm sure that one could, yes, I mean, the yield may be lower for some random reason.
Right.
Well, it depends on what reactions you allow, and in this case here, there's only one kind.
Yes.
So efficiency and yield all depend on what rules you allow.
All right, let's take a look. What other things have people got to show here?
Jason has some stuff.
Oh, wow, what are these? What are these creatures? All these names and the fact that we even don't recognize them has anybody cross-checked between our molecule names and our spell checker? That sounds like
I don't
guess
think
so.
so.
I was to say, in the time that I've been here, the chemistry team hasn't thought about that.
You should communicate with the spell checking team, because I mean, we
With
might as
the-
well. It's silly. Those words are hardly close to any other words. Nobody's going to make a typo for one of those things. That they should be added to the dictionary, I would think. Okay, so what is this creature?
So this is a molecule that nature makes to move iron from the environment to the inside of the cell.
Okay.
And this is there's a whole family of these, but this is a circular one, and it has, you know, a symmetric shape as that first plot shows. And then here's the two, you know, another plot showing the same structure. It's different conformer of it. And then here's the 3D representation to help.
Where does the iron go? Does the iron get stuck in the middle here somewhere?
Yeah, the iron gets stuck in the middle, and we'll see that just a little bit
Okay.
lower. And so if you open up the next bullet, so therefore complexation reactions. Yeah, there you go. So here's
Wow.
the iron version. So iron with 6 waters around it, and it reacts with the big thing, and you get the structure that you see there.
So this is all covalent bonding story. There's
Yep, that's right. And so what's interesting here is how you're displacing all those waters, and you're removing 3 hydrogens from the big siderophore. And the question is, how do all these bonds form? And there's a variety of different ways that it could happen.
And I see, this is where plutonium is substituted for the iron or something? Or what?
Well, so there's the iron on top, and now here's the plutonium. It has 9 waters rather than 6. And then if you scroll down a little further.
What is the valence of plutonium?
In this case, it's 9 coordinate.
Okay. Okay. Is that, I mean, again, naive question, but is that obvious from the periodic table? If you saw where plutonium was, would it be obvious that this would be a...
Not necessarily. That's the problem. When you get past carbon, you can have coordination numbers from 2 to 16.
Explain why?
Well, in the case of the metal here, you've got F and D orbitals that can hold electron density. And so each of these water molecules is dumping electron density from the lone pairs on the water into the orbitals of the metal. And so you can have configurations where you have, you know, in this case, we have 9. Other metals will have more if you have different ligands besides water.
So are you telling me that the whole valence theory thing only works for S and P orbitals?
Pretty much. That's
Yeah.
Valence
That's a
bond
shocker.
theory. Oh no, yeah. It's a very particle-oriented picture of an object, the electron, which is, you know, both a particle and a wave.
Yeah.
So wait a minute. You're saying as soon as you get into these higher orbitals,
Mhm.
where there are more possible electron configurations, that there are many different ways in which you can do covalent bonding, in other words, what you're saying is that in the S and P orbital case, that, you know, if you think about the orbitals in terms of spherical harmonics or something, they just have sort of 2 knobs on them or something. They have a small number of knobs. But whereas what you're saying is when you get to higher harmonics, then you can essentially have the covalent bonding happen in many of the different. So in other words, if you plot the orbital, you can have the places where there is high quantum amplitude or something as a function of angular position. You can say you can kind of fit the covalent bonding. You can fit the exchanged electron into many different kind of holes in the angular distribution of the. I'm not saying this very well. Did that make any sense? I mean,
it did, and you're right. And if we were to look at the P orbitals have 2 lobes, D's get up to 5, or 4, and so you can get those lobes then become, if you will, houses for a pair of electrons to interact with each other.
I see.
And then you can have various linear combinations.
I was
Yes.
just going to say, kind of like, one shouldn't take these lobes too serious,
Yeah, no.
because there's no reason to assume nature diagonalized HS squared and LZ. That is nice for convenience, but
Yeah.
nature might well diagonalize in parabolic coordinates where we have totally different quantum numbers.
Right.
I see. So you're saying that the question of what the actual states of the atoms are, and this relates also to this sort of continuous measurement of atoms and things. There's no reason to think that the eigenstates correspond to that the thing is in correspond to these convenient Cartesian or
So the eigenstate is fine for H, but what physical reason would the molecule have to, because energy cannot be created and taken away, but why should LZ be diagonalized?
No, I understand that, but I mean, when you decompose when you have an energy, you have normally in a magnetic field or something, you would split those different things, right?
Yeah.
But
without magnetic field, they are degenerate, so we should allow arbitrary superposition rather than a randomly selected
I understand
operator.
Cartesianish thing.
Yeah.
Right. Well, actually, it isn't. It's a spherical tensor, I suppose. But I see. So, but the point that I was making is my understanding is in the sort of quantum theory of chemistry, you imagine that the molecule is somehow in an eigenstate because it is being somehow continuously measured by the environment. That is, that's why we can draw a picture of what otherwise we would have no way to validly draw one of these diagrams with the atoms in particular positions. Because
I think not quite.
Okay.
Okay, so it is an eigenstate because of energy conservation. Mm-hmm. It is in a localized version because of continuous measurement. Otherwise, the center of mass would slowly flow apart.
Okay, but hold on. In an s orbital, for example, in J equals 0, the thing is going to be spherical, except that we might very well draw our molecule
after separation of variables.
Okay, fair enough.
That is the critical point. The center of mass part would normally flow apart, but the center of mass part gets measured continuously by the infrared field and collapses.
So wait a minute. Let's say we've got a hydrogen molecule. Okay. Yeah. Then there is are you saying that there's a J equals 0 configuration of the hydrogen atom, a hydrogen molecule, that would normally have, but you're saying when we separate the variables for the two hydrogen atoms.
Yes. We get internal degrees and external degrees. And normally we totally forget about the external ones. But the wave function for the external will not be staying localized. Why would it? Without the external field.
Wait a minute. You're saying that yes, right. I mean, well, you're saying why would the hydrogen molecule be in a particular orientation? Is that right?
No. Like simplest one, just take one hydrogen atom. So we have the electron and we have the proton in the middle. The first thing what we do is we go to a coordinate system that's the center of mass system. And then we typically forget about the center of mass part and just do the relative one. And the relative one gives us then bound states. But still we need some kind of wave function for the center of mass part. And this is free because it's not bound by anybody. And this one would unfortunately slowly flow apart.
What do you mean by flow apart? I mean, the thing, it can be anywhere in space. The hydrogen...
No, like the free evolution of a particle flows apart.
What do you mean by flows apart?
Initially, it's Gaussian. You wait, and the Gaussian has a bigger half-width.
In the Schrodinger equation?
Yeah. Because
it's a diffusion-like equation?
Yes.
What's the time scale for that happening? What's the effective diffusion constant? It's a complex diffusion constant, right? Or imaginary diffusion constant?
Yes. For small things, pretty small.
But it's IH bar, equals, I mean, so it's something like the de Broglie wavelength. What is it? We should be able to work this out. But what is the thing that determines, you're saying-
The mass. The mass is the only parameter you have.
So it's a de Broglie time, effectively, de Broglie frequency.
Yeah.
Has to be what determines the diffusion constant.
Yeah.
Okay. So and that de Broglie frequency for a typical atom is what? Wolfram Alpha must know this.
Tiny fraction of seconds.
Okay. But so that means that what you're saying is that you're saying a Gaussian wave packet will be, you try to localize the atom,
Yes.
but soon the atom will no longer be localized just by virtue of the Schrödinger equation.
Of the center of mass part. Yes.
Right. Okay. So that means the atom is fuzzed around.
Yeah.
And then how does that affect? And you're saying, given that.
But this doesn't happen because the infrared field permanently measures the thing.
Okay. So normally you're saying the hydrogen atom would just be I see. So you're saying, I've got to picture my ball and stick model of a molecule, but in fact, one of my balls would gradually just diffuse away, were it not continuously measured.
The whole thing is, not a part of it, the whole. Because the internal ones are all, basically, the internal degrees of freedom are proper bound states with finite localization. It's the whole thing that is not fixed.
But that's just its position. Why can't I?
No, it's not its position. It doesn't move. It just spreads out.
Okay, you're saying that the amplitude, I see what you're saying. You're saying that the whole thing, right, I get it. The whole thing just sort of diffuses away in amplitude space.
It gets thinner and thinner and bigger and bigger.
Okay, so now, but what you're saying is that is effectively continuously measured.
Yeah.
And that, walk me through that. So you're saying is it a photon field or is it?
It's the infrared field. We think it's the infrared field, basically.
But why isn't it? I mean, in practical matter in chemistry, there's a high collision frequency between molecules.
That's also do. I was thinking on a single one in vacuum. Yes, in of course, environment is extremely efficient in localizing and measuring.
Okay, so you're saying that even in a vacuum, okay, so there's photon absorption, photon re-emission. Why does that? Explain why that does anything. I mean, in other words,
because basically it is not an isolated system.
Yes.
So the Schrödinger equation was a wrong assumption from the beginning.
But can one actually compute? I mean, so let's imagine that you turn up the heat, so to speak, from the environment. You increase the photon density in the environment. Is there a measurable way to see that there is sort of more measurement, more maintenance of localization? In other words, if you turn down the heat, so that there are very, very few photons, is there a way to measure the delocalization of the atoms?
I don't think so, because I think there's always enough infrared available to get a thing collapsed.
That's very, I mean, so you're claiming that as a practical matter, even in the darkest places, I mean, forget the cosmic microwave background, but assume you put it in a box, so there's no cosmic microwave background. You're saying there is no box quiet enough that you get delocalization.
Right.
Interesting claim. But so why do we see quantum mechanics at all? If that's happening, why isn't everything always being measured all the time? You're saying it is being measured, but the time scale for measurement is still long compared to the time scale for other small quantum effects.
Correct. Like the time scale is days for the moon or something like this.
Time scale for what is days? Sorry.
For the moon to flow apart.
Yeah, I understand. But the time scale, I need to understand this more. I need to understand this in the context of our models. James, this would be a good thing to talk to Xerxes about. He might have thought about this.
Yes. Okay.
I want to understand this because I think that we should be able to understand this with some clarity in terms of our multi-way graphs and so on. This would be a good thing to see why. I mean,
Summer school
think-
student project?
Too hard.
Too hard?
Say too big.
Research affiliate project?
Yes, possibly.
Okay, good.
I mean, this. What you effectively seem to be saying, Michael, is that, I mean, there's an analogy, like in our models, space-time is knitted together by continual interactions. You're effectively saying, I think, I mean, the implication is that objective reality is knitted together by these continual interactions.
Yeah, I think that's a correct statement.
How lovely. I mean, that would imply, in the world of our multi-way graphs and all these kind of branchial space things, that's a rather lovely idea. That in other words, that the existence of space is a consequence of yeah, okay. I need to understand this better. This sounds very cool. All right, but this is irrelevant to our chemistry. How do we get talking about this in the context of the chemistry? We were talking about, we're back to
The orbitals.
Yeah,
Yep.
we're orbitals, right? Okay, I was trying to understand orbitals.
Yeah, we
Okay.
were moving from a valence bond picture where you're counting 8 electrons to a molecular orbital picture here, and the molecular orbitals are actually an approximation to the electron density.
Fine. Okay.
And that's where we got off. Into
Okay, that's where we zoomed off into quantum measurement. Okay, so this little cage allows one to capture an iron or capture a plutonium. Is that the basic picture?
That's the idea. Yep.
Okay.
And so what I was interested in is how those bonds form when you bring the two together, and that's what we were looking at. And this sets you up for a case where you have a metal, in this case iron, with water, and you're looking at all you have these small reactions, and are they happening where you're forming 2 bonds at once, or you're looking at the case where you have 1 bond at a time, and
Okay.
then you can map that all out.
So did you make the multi-way graph someplace here?
No, I did not. I ran out of time.
But you think you can, and it's going to show a bunch of reaction pathways. And is there some way using NMR or something like that where you can measure the different configurations of what happens, or is that what can you figure?
That's the tricky part. I don't have a good answer for you on that one.
Is it the case when you have these things where there's a sort of distinguished atom knocking around, am I right to think that NMR is a potential technique for seeing the environment of that atom and so on?
To a degree, but with the metal atom present, that's going to probably broaden all the signals in an NMR spectrum.
I see, because the NMR is primarily looking at hydrogens.
Or, or depending on the magnetic field and the frequency, the radio frequency that you're using, it could be looking at carbons or nitrogens or oxygens.
Yep.
But hydrogen and carbon are the 2 most common ones.
But you can't tune it to iron or plutonium. I mean, it depends on there obviously is a nuclear magnetic moment of plutonium, for example.
Yeah, and it depends on their spin also, I think.
Obviously, right. I mean, it's the Bohr magneton, right? It's the analog, whatever it is, times the spin, right? It's the H bar times the spin. But that's interesting. I mean, so okay, look, the basic bottom line here, as we zoom back, okay, so we basically seem to understand more or less how to make token event graphs for chemistry.
Yes.
It would be nice as a piece of sort of gravy or something to be able to actually try and use automated theorem proving to find, pathways here, just because that would be the analog of synthetic chemistry, so to speak.
Yes, very much so. Yeah.
But so then, and we don't understand how to get rate constants, and those are really hard. So we're not, so in a case where we might try to do molecular computing, we have to have a case where, for whatever reason, all the rate constants are non-zero, and we think they're comparable, and we're not worrying too much about them. Because if we had to compute them all,
right?
I mean, that's an actual chemistry question whether we can find that. But then the question is,
Well, wait, how common or uncommon are those? Bob, Jason.
Yeah, I mean, so like in this big picture that you had at the top here, would it be the case that most of those pieces actually happen up here? Do most of those?
Probably the first two, probably a lot of the third tier could be made. The fourth tier, some of them might not be able to be made because of geometry and stuff like that, where you can't get the parts close enough together to add a new piece.
Yeah.
I'd have to look at some of them more closely. They're just too small to see where the
Yeah,
double
okay.
bonds are.
Okay, but so you know, one of the questions is going to end up being because that would be, in order to do non-trivial computations, we're going to need eventually long chains of chemical processes.
Mhm.
And, you know, in the case of biology, it's using, I would assume it's using enzymes as its way of kind of just making stuff happen, you know, as its way of catalyzing these long chains of reactions. Is that right?
Pretty much, yeah.
And so for us, in these, you know, we think these are liquid state reactions that we're looking at here, as opposed to sort of enzyme state where the thing is aligning itself, you know, or as opposed to a solid catalyst or something where it's effectively a surface effect. So my question would be, if we want to do something that involves a long chain of reactions, what's the best way to do it? Liquid phase probably isn't going to make it. Is that a true statement? Because you're saying in the liquid phase, it's too easy to get molecules that flop around and prevent sort of, you know, fail to expose the places where actual reactions could happen.
Yeah, that could be part of it. Also, some of them, you know, in this graph here, if you look at the ones on the periphery, they're getting big enough that they might not be very soluble anymore, and therefore would form a tar on the bottom of the flask and wouldn't be available for reaction that way.
You know, I love that this is, you know, we're at some level we're doing mathematics or computation, but in the end,
Yeah.
the thing precipitates out and makes
That's
a tar
right.
at the bottom.
That's right. Yeah. We got to work. If you want to reduce this to practice in the lab, you know, those are considerations.
Well,
Absolutely. Yes.
This is what
Yeah.
this is what I'm expecting. This is why I actually want to run some of these things in Emerald's infrastructure and see what happens. But okay, so what does it mean? Okay, what makes something not soluble? What makes something soluble? Okay, explain.
It's too heavy, gets too big.
Well,
and
to be
it's not soluble.
to be insoluble, that it sticks to other copies of itself, and
Well,
so it
more
solidifies
yeah.
effectively.
Effectively, yeah. It might not be crystalline, but you end up getting a particle, and more stuff accretes to the surface.
What's the difference between a tar and a gloss?
A tar is probably a soft glass.
Okay, so it's just some amorphous, you know,
Yeah,
combination.
amorphous. Yeah, mess.
Okay, all right. So you're saying that the issue is that at a certain temperature, the longer the molecule, the less soluble it's going to be. Is that right? And that therefore, when the molecule is big, well, no, you're saying because the temperature is higher, the molecules will presumably get broken apart. Or am I wrong?
That could also be an issue. Yeah.
Oh, I see, but the molecule will actually, you know, decompose. But
Yeah.
no, I was thinking of what would cause the thing to not precipitate out as a tar.
Well, basically, the interactions between the solvent molecules and the new molecules you've made have to be, those interactions have to be, if you will, exothermic, so that or more favored than the molecule making covalent or making van der Waals interactions with itself and starting to form a solid.
Yeah.
I see.
Yeah.
Okay, but
Or
and what's the
if-
temperature dependence of that likely to be? Or is that not obvious?
I don't think it's not obvious to me.
But
Yeah,
as
I
the
was just saying,
molecule
I've never
gets
thought about
bigger,
the valence. I've never thought about the temperature dependence of a van der Waals interaction.
Yeah.
I guess you could think about it as it's in the same realm as the temperature dependence of a hydrogen bond in some bio thing.
yeah. But I mean, Van der Waals interaction is just, I mean, as I understand that, from at least from the quantum electrodynamics point of view, which might not be the chemistry point of view, that's, I mean, it's some vacuum fluctuation. It produces a temporary dipole moment, which then induces a dipole moment in the other molecule, and that's how you get the forces.
The hydrophobic attraction. Yeah.
Right. But so then the question is, why? I mean, I see. So if the thing has a great big dipole moment, does that make it more likely to have large van der Waals forces? Is that what determines it? And I mean, that might not be, if it has a great big dipole moment, it may be that the vacuum fluctuations will do different things to it as well.
Yeah.
Well,
But then it would be
depends on the
very
solvent, right?
soluble in a polar solvent.
Yeah, I was just saying, yeah.
Yeah. And as soon as you start using nitrogen and oxygen in these molecules, that means, you want to use polar solvents, and they tend to, well, they could be more soluble with a solvent, but they would also have more hooks to use on each other to stick.
I see. But
Yeah.
polar means what? That it's like water or something, where the thing is.
That there's a dipole, a local dipole.
On the molecules.
Where you've got
Why
more
does-
electrons in one part than another, basically.
Okay, naive chemistry question. Why does that help with solubility?
Well, with a polar solvent, you can solvate the water, or whatever the polar solvent is, has dipoles also, and you can get favorable dipole interactions with the solvent molecules, which makes that stable, and therefore they would be soluble.
I see. Okay.
Yeah.
All right,
But they could also, form stable dipole interactions with other molecules, other solute molecules, and then you start getting crystallization and precipitation.
Right, but knowing how these things, I mean, let's pick a random molecule like this. How that thing makes a crystal is kind of non-trivial, isn't it?
These guys, yeah.
I mean, that's a separate question, which is also quite interesting. And I mean, I don't know whether we've ever, because that relates to this other problem that I've been looking at about these, random tilings and so on. That is, when these form a crystal, okay, next naive question. When they form a crystal, what forces hold, for molecules like this, what makes them crystallize? Because normally, I mean, like a sodium chloride crystal, it's all ionic stuff.
It's all ionic stuff, yeah. Charge attraction. Here, it would be the hydrophobic interactions, the van der Waals interactions.
So there are crystals that form from van der Waals forces.
Yeah. I mean, things like benzene will crystallize.
I
low
see.
enough
There's nothing
temperature.
ionic about it. But so is it the case whenever in organic chemistry, when things, become solid, okay, next naive question. Do they all form crystals, or do some of them just make amorphous stuff?
Some make amorphous stuff, yeah.
And you can't get them to crystallize, or they
Yeah.
just
They're some things can be very difficult to crystallize, yes.
But if you have the right nucleation and things, and you have the right conditions, and you kind of let the thing go slowly, will it then crystallize, or are there ones that just never crystallize?
It's an art, and you can get it to happen. We have a very big electrical storm here, so I might get cut off by losing my internet. So just to let you know.
Okay.
Yeah, calling crystals an art form. So I mean,
Yeah.
Yes. Right. Well, okay. This is all interesting stuff. Do we need? We should wrap up here. But anything we need to say in terms of roadmap? I mean, we've got.
Yes. I think so. A few additional steps in terms of how we can direct this towards molecular computing would be helpful. So there's this, automated theorem proving case, I can discuss that with Nick. But in general, okay, so we have these tags. You know, what next? How do we get closer to molecular computing?
We need to think about this. I mean,
Yeah.
I think we need to think a bit more. I think it will be interesting to look at the kind of QSAR embeddings of, if that makes any sense. So that, you know, whatever the embeddings of these graphs. For example, if we just took this graph and we know, I don't know, boiling points of these things, what would this, you know, roughly? I think that would be interesting to see.
What would
I don't
the
know
feature space plot be?
Yes, quite right.
Okay.
For a feature like, you know, that would be I mean, because when we try to reduce this to practice,
Yeah.
that will be important. So I'm just getting some sense of that, because in the case of, you know, in the case of theorems in mathematics, the only way we lay theorems out in theorem space is pretty much through their entanglements, aka common ancestry. We
Yes.
don't have a good way of saying this formula is this distance away from that formula. But in chemistry, there are some intrinsic properties of these molecules, like boiling points and things. So we do have some other alternative coordinate systems. I guess that's the question: is what coordinate systems can we use?
Yeah, right. Okay.
And molecular fingerprints, whatever those might
Yep.
be, represent some coordinatization of the space of molecules. And it would be interesting. How do those work typically? Those molecular fingerprint things?
Yeah, basically, they're graph invariants, counts of graph substructures of various sizes and shapes.
So it's kind of like these Wiener indices that are used for boiling point estimates and things. Is that right? Or
yes. Yeah. Those were the simplest early ones.
Okay. Okay. Fine. So I mean that's a way that we can coordinatize molecular space. That would be interesting to see.
Yeah.
Now another question. Okay. So you know our big hint is biology, and I know we're running low on time, but let me just see whether I have one thing here, which I was hoping. Does anybody happen to know where what was that name of that thing? What was the name of the
But the game?
The game. What was that called?
Was it Nanoscape?
Yes, I think that's right. Let me see whether this is installed on this machine.
Yeah, Nanoscape.
This could be very scary. What's about to happen?
Yeah.
Let's see.
Yeah. While you're looking for that, the other idea that you mentioned earlier, Stephen, that I liked was compile computation into graph rewriting and then translate that to chemical reactions.
Yes, that's interesting.
If we can find a nice bijection there, that sounds like something that's feasible.
Right. So the question is, in graph rewriting, how do we do practical computations with graph rewriting? Gosh, I tried to do that back in the mid-'80s for a way of doing parallel computing, but I didn't really understand it very well. I mean, I think I understand it better now. Let me see. Can I start this game? Hold on one second. Nanoscape. Oh, for God's freaking sake. No, my password of my virtual machine is help. That's crazy.
Help is too simple, Stephen.
No. I know. What the heck is
It's getting late.
my virtual machine? That's crazy.
But don't say it out loud. We're being recorded.
I know.
It will be bleeped over.
I'm asking Roger.
Yeah. Okay. Fine. If he can, if it's my LDAP password, it doesn't appear to be an LDAP password. I wonder whether it's in my password manager.
Don't screen share that.
I'm not screen sharing that. I'm nope, not there. Well, okay, I really want to, by the way, can you see that screen, or can you see whatever it is, the lake or whatever it is?
Yes.
Yeah.
Blank out. Okay, fine. So if we can only log into this thing, I have no idea where the lake is, but if we can only log into this thing, we should be able to see this nanoscape game. Somebody might have to text Roger.
Yeah, I'm reaching out. I'll try to get him as soon as I can.
Okay. Okay. So,
Graph rewriting.
right, graph rewriting, compiling things into graph rewriting. I mean, we've already done a little bit of that in the physics project technical introduction. I already looked at some degree of, turn combinators into graph rewriting and so on. But I consider that, okay, the case that I really want to look at is the analogy with molecular biology and the question of whether, so in this graph, okay, in this graph, normally in chemistry, we were just talking about what is the concentration of each molecule, but this graph has a lot more information in it about, so the question is, okay, so for example, here's an example of a question. In chemistry, the fact that there is this event that leads to other molecules, etc., the fact that there is a holonomy, the fact that there is non-trivial topology in this graph, what consequence does that have for chemistry? In other words, the fact that there are two different paths that get to the same thing. That's the question. That's what we found in the case of games, things like, the Towers of Hanoi. There are multiple different topologically distinct pathways that get to the same result. We don't really know what the significance of that is in mathematics either, but that's a feature of chemistry that I don't know whether anybody, that's perhaps something that is not, that's a question of the dynamic structure of the token event graph that would be irrelevant to synthetic chemistry, I think. Or would it?
No, it would be very relevant because that's your number of steps involved in your, in your synthesis plan.
No, but what we're saying, Bob, is that there are two different paths, right? They both lead to the same, both roads lead to the same result.
Right, but one path is longer. It's likely to produce your result in lower yield.
Yeah, I understand. But what you want then is the winning path. That's all you care about. The fact that there are multiple paths, albeit of different lengths, that get there is not something you care about. Whereas I'm saying another feature of this network is that there are multiple paths. And the question is, does that matter?
And in terms of relation to biology, I do wonder if either the molecules that organisms commonly use or the ones that we find in our biosphere, if those are ones that also enjoy some high density in metachemical space, like they arise through many ways. They have a high,
yeah, right. I understand.
Have a high degree.
So high utility, as it were.
Well, potentially utility or synthesizability.
Yeah.
Right. That is a good question. I looked in the NKS book, for example, I looked at, okay, so here's a good question, actually. For a picture like this, which ones are in chemical abstracts? Are all of these molecules in chemical abstracts or only some of them?
I would say some of them.
Okay.
Are these tar-like, precipitates at the periphery? Are they really going to be in abstracts?
I don't know.
It's a rhetorical question.
Well, originally abstracts would only give a registry number to compounds that were actually made, but sometime in the 80s or 90s, they started allowing hypothetical structures as well into abstracts.
Okay.
Well, that's because the computational chemistry community came about, and they wanted to index the things that we were talking about.
Yeah.
Right. But okay. But so the thing we could potentially do here is annotate this picture with which ones actually occur in biology, for example. And that would be kind of interesting to see because that gives us, that is the analog. Oh gosh, all these things are so freaking connected.
Yeah.
In metamathematics, right?
Yeah.
We can generate all the different theorems, but only some theorems have names.
Yeah. I sent an email about that last night. Yeah, it's the same question. Yes, it's the exact same.
Right. In other words, we can generate all these molecules, but only some of the molecules are molecules that we care about.
That's right.
or that biology cares about.
That's right.
And biology has had, its preferencing mechanisms are a little different. Let me just, one second here. I'm sorry. I'm reminded of, by the way, in terms of observer theory. I don't know if I told you this, but I took that particle detector on a plane last weekend or something.
Yes. Fireworks, right?
It's just spectacular number of particle events.
Yeah.
Which it's just
At 35,000 feet.
Yeah.
Yeah.
And including ones, and Michael may be able to recognize these. I don't know. I haven't really looked at this yet, but where the heck did I put this? This is not one of those things that one immediately knows where to put it. Oh, here we go. Let me just see here. Oh no, I thought this was. I thought Roger had sent me the thing. Oh well, I maybe can't show this here. But there are a bunch of V's, which I think maybe other people. I think those are strange particle production. I think those are the so-called V particles. Those are associated production events. But I've never seen a strange particle in the flesh, so to speak. Or, if there were strange particles in this little particle detector sitting on my computer, then I'm sure there were ones being produced in me by cosmic rays while that was going on, so to speak. But anyway, it's kind of interesting. You can really see actual, lots of actual particle events. Okay, that was irrelevant. But anyway, so annotating this.
Oh, yeah,
go ahead.
No, go ahead.
We have PubChem. You can usually look this up programmatically, right? We have to do that. So.
Yeah, sure. Right. Okay, but then, continuing the discussion of biology, and the reason I wanted to show this nanoscape thing is because it is trying to show a version of what's happening in the cytoskeleton and other kinds of, in a sense, what one might call solid directed reactions. And I'm trying to get some sense of, in biochemistry, molecular biology, how many interactions really happen in this kind of liquid phase chemistry type mode, and how many of them are organized by membranes and other sort of solid structures. Maybe
I think the vast majority that sustain life are organized.
Do you know, I think this thing had no password. That's embarrassing.
All right.
Okay, let's see what happens here. Oh my gosh. It's making weird noises, but other than the weird noises, it's a black screen. Come on. Skip the weird noises. I just want to see the inside of.
Okay.
Oh no. What's happening here? Is that help? Where's my mouse? Oh, here we go. Okay. Okay, we got weird, eerie sounds, but I just want to see where. Help! How do I get anywhere? What do I do here? Okay, how do I switch off the stupid eerie sounds? I guess I just say mute. It's a good way to do it. Okay. So what are we seeing here? So we're seeing a cell membrane with a bunch of, oops, did I? You know what? Can anybody, hello, talk to me? Anybody there?
Yeah.
Okay, I don't think I can. I think if I mute it,
you can't hear us. Yeah.
I can't hear you either. Let's just see. Do we have any options here for, I wonder if the virtual machine can have its, oh, wait a minute. I see a microphone thing up there. Where's my mouse? Where the heck is my mouse? I'm really confused here. But so Somebody give me a guided tour of what I'm seeing here. Is this? Does anybody know what? I mean, so this is a cell membrane, and these are molecules on the cell surface, right? Attached
Pieces
to
of
cell
proteins that are sticking out of it, probably. Yeah.
Okay.
Yes.
And that great big hole that we need to see now, I can really use Twitch properly because now I'm streaming some video game. Okay, what are those holes? Oh God, for God's sake, why is this thing?
Canals where the
Probably
interaction happens.
pores. Yeah.
Yeah.
But I would expect a lot of
Ion
protein
canal.
around them as well.
And what are those stringy things? Those are pieces of the cytoskeleton? Those are like,
Well, if we're in the cytosol, probably, but maybe it's more like collagen fibers on the outside between cells.
okay, so how do we think we get into the cytosol? Do you think we can just
Oh,
dive?
go down that hole, dive in the
Yeah,
hole.
I know. But how do I get in the hole?
I
I
don't
think I
know.
should have read. I think I should have
You
read.
get
have
your
to move
putter
this,
out.
Keyboard, it says.
Yeah, it
right?
looked like WSAD. Maybe try to press W.
Somebody on the chat probably knows.
No, it says in the beginning it showed how to navigate, right?
Yes, I know, but I wasn't paying attention to that.
But can you go into the interior?
Well, I don't know. We don't know whether they've got
Well,
imagery there.
I don't know.
Okay, so this is not as exciting as.
Jesse could probably help.
You're right.
You could fly an Arduino down the hole.
Okay, this isn't very exciting. So this is just the surface of the cell. I want to see inside the cell. Now what's happening? Where are we here?
Can you look up? You're kind of staring at the.
Well, how do I look up? I'm pressing the S.
What does your mouse do? Does it control?
Well, my mouse is lost. My mouse is just somehow. I can't. I think my mouse has been captured by the virtual machine.
But
you would have to hit
Oh, wait a
like
minute. Control Alt to free cursor. Control. What's an Alt? Oh, wow. There we go. I got it. Okay, fine. Okay, so then. Oh, no. What's it doing? Okay, so maybe I'm. Oh, I see. I have to press Control Alt every time I want to free the mouse. Okay, well, this is clearly not some. Not. What is happening? Help! Well, okay. We clearly need to have a little bit more. What's that? Is that a bring up the keyboard? No. There's got to be some controls here that let us do something.
Why do they make the lighting so wild?
Well, I mean, I don't know what this project. Help. Okay, well, this has not been as successful as I'd hoped. I think it's time to close this Windows window. No, it won't go away. Help. What the heck? It refuses to suspend.
Metastasis. Yeah, it won't die.
Unable to suspend Windows 10 because there isn't enough. What the heck is this? It says unable to suspend Windows 10 because there isn't enough free disk space. Okay, I think it's time for us to wrap our meeting here.
Yeah.
This is
go.
horrifying. Okay, see you all soon. Thanks to folks on the live stream. To be continued.